Indeterminate forms and L'Hopital's rule. Let's read the following definition that defines two types of indeterminate forms. Let's suppose that f and g are two functions that go to 0 as x approaches a, and h of x and k of x are both functions that go to infinity as x approaches a, and a here is either a real number or plus or minus infinity. Then the limit as x approaches a of this quotient f over g and the limit as x approaches a of this quotient h over k may or may not exist and are called indeterminate forms of types 0 over 0 and infinity over infinity respectively. So this one here is called of type 0 over 0, indeterminate form of type 0 over 0, because the numerator here goes to 0 and the denominator goes to 0, right, as x goes to a. So this is called of type indeterminate form of type 0 over 0, and for this one that guy is going to infinity upstairs and downstairs infinity, so this is called an indeterminate form of type infinity over infinity. Recall, indeterminate form is we've seen it before, especially in Calc 1, and what it means that the value of the limit cannot be determined, right? It's just a symbolic monstrosity that's meaningless unless something can be done to quote-unquote simplify the expression before letting x become a, right? And how did we handle the case when the that quotient was a rational function? This function here, the quotient, is a rational function, meaning the upstairs guy is a polynomial and the guy downstairs is a polynomial. We used to employ algebraic manipulations. For example, in this case, in the first bullet, I'm taking little a to be 1 here, right? And f of x to be x squared minus x and g of x to be x squared minus 1. Each one of them goes to 0 as x goes to 1. And this is of type 0 over 0 then. And what we did, we factored x minus 1 upstairs and downstairs, and we simplified by this common factor. And then we let x go to 1, and we found the value of the limit. When a is infinity, this is an example of a rational function. So upstairs x squared minus 4, downstairs 3x squared plus 5. We used to factor out the highest degree of the numerator of the denominator, so x squared, right, upstairs and downstairs, and then once you simplify, you let x go to infinity and you find what the limit is. Okay. However, these algebraic techniques do not work for limits such as this. The limit as x goes to 1, ln x divided by x minus 1. And also, these algebraic techniques do not work for such a function, for such a limit. Okay. And also, these algebraic techniques did not work when you were trying to evaluate the limit as x approaches 0, sine x divided by x, right? This is an indeterminate form of type 0 over 0, right? Because sine x goes to 0 as x goes to 0, and x goes to 0 as x goes to 0. So this is indeterminate form of type 0 over 0. But to find the value of the limit, which was 1 at the time, you used a pure trigonometric argument, right? So you didn't use any of these algebraic techniques that we were talking about. So the point is, these algebraic techniques did not work in a uniform fashion, and these are examples where these techniques cannot be applied. However, there is a technique which can handle those limits, and it's called L'Hopital's rule, which is due to the French mathematician Guillaume François Antoine de L'Hopital, who lived in the 17th and 18th century, so between those years. And it goes like this. Assume that f and g are differentiable functions. Remember, differentiable functions means their derivative exists. And since g prime exists, let's also suppose that g prime is not 0 on an open interval containing a, except possibly at a. So under these conditions, let's also suppose that the limit as x goes to a of the function f is 0 and the limit as x goes to a of the function g is 0. So f approaches 0 as x goes to a, g approaches 0 as x goes to a, or that f approaches infinity plus or minus as x goes to a, and g also approaches infinity as x go to a. In other words, I'm talking about this this quotient that we were discussing above, such a quotient here. Either I have 0 over 0, right, if you assume both of them go to 0, or I have infinity over infinity, right? So this is what this is saying. Okay, so you see it here at the bottom of the screen. In other words, we have an indeterminate form of type 0 over 0 or infinity over infinity. Okay, but don't forget, the assumption is f and g are differentiable, and g prime is not 0 in an open interval containing that limit point a. Okay, except possibly at a. Then the rule says the following: the limit of that quotient is exactly the same as the limit as x approaches a, the same value, of the quotient of the derivatives, okay, f prime, g prime, if the limit on the right hand side exists or is equal to minus infinity or plus infinity. Okay, so these two things are the same. This is what the rule says. This is what L'Hopital's rule says. So the limit as x goes to a of the quotient f over g is the same as the limit as x goes to a of the quotient of their derivatives. Okay? Comment number one, we are not talking here about, on the side, we're not talking about the quotient rule for differentiation. Let's read comment 1. Notice that when using L'Hopital's rule, which is this formula here, we differentiate the numerator and the denominator separately. We do not use the quotient rule for differentiation. Okay, so this is not the quotient rule. This is just differentiating the numerator and differentiating the denominator and taking the quotient, the quotient between the two. Okay, so this is comment number 1. Comment number 2. L'Hopital's rule is also valid for one-sided limits and for limits at infinity or negative infinity. That is to say, the x of x going to a symbol, this symbol, so such a symbol may be replaced by any of the symbols x is approaching a from the left, x is approaching a from the right, x going to infinity, or x going to minus infinity. Okay, and we're not going to discuss the proof in this video about L'Hopital's rule, but I'll be very happy to discuss it with you if you contact me and if you are interested. Okay, let's see this this rule in action. Actually, let's apply it to these two limits that we were discussing above. So that's going to be the first and second parts of the next example. So that this example, which is about finding the following limits. The first one is the first one I had above. So the limit as x approaches 1, ln x divided by x minus 1. So observe that ln x approaches 0 as x approaches 1, and x minus 1 approaches 0 as x approaches 1. Correct? So this is an indeterminate form. This is an indeterminate form of type 0 over 0. And L'Hopital handles such a situation provided I verify the conditions, right? What are the conditions? I need the two functions to be differentiable, upstairs and downstairs, and the guy downstairs to be different than 0. And I want these two to happen, these two highlighted conditions to happen on an open interval containing a. So as long as there exists an open interval containing a where these conditions, the highlighted ones, happen, except at a, it's okay if this doesn't happen at a, but they happen in a neighborhood, in an open interval containing a, then I'm gonna be able to apply the rule, right? Okay, so let's go back. Who's f, who's g in our discussion? F is ln of x, that guy is f of x in L'Hopital's rule, and that guy is g of x, correct? And this guy here is the a in the formula. Okay, clearly f of x is differentiable in an open neighborhood containing a. In an, again, neighborhood, by neighborhood I mean interval, right? So f of x is differentiable in an open in some open interval containing 1. Correct? ln of x, how do you graph ln of x? It's a graph that looks like this. Correct? I'm talking about 1. Certainly in a small neighborhood, small neighborhood of 1, let's say this neighborhood, certainly the function is differentiable here, right? I'm talking about this part. Certainly this function is differentiable. You have tangents everywhere here, right? Okay. And x minus 1, similarly, this is a line, so certainly it's differentiable. It's differentiable everywhere. In particular, it's differentiable in a neighborhood containing 1. And this is 0 at and only at 1, right? And that's okay according to the formula. That's okay, except possibly at this number a, you're allowed to have failure of such a condition, correct? So the conditions are verified of L'Hopital's rule, and as such we can employ it. And what does it say? And what does it say? Let me just erase all of these. Well, it says that this is then equal to, and let me just label this equality HOP for L'Hopital. It says that this limit is the same as the limit of the quotient of the derivatives, right? So this limit is the same as the limit as x goes to 1 of the derivative of the guy upstairs, right? And divide by the derivative of the guy downstairs. So the derivative of the guy upstairs divided by the derivative of the guy downstairs. Okay, and what's that? What's the derivative of ln of x? It's 1 over x. It's 1 over x. And what's the derivative of x minus 1 with respect to x? It's 1. So we get the limit as x goes to 1 over x. That guy is 1 over x, and this is simply 1. Correct? So this limit actually equal to 1. And what does this mean? This means as x approaches 1, so as x approaches 1, if that's the number 1, as x approaches 1, it's a two-sided limit, right? So as x approaches 1, the function approaches the value 1. So the function is going to approach the value 1. The function is not defined at 1, right? This function here is not defined at 1 because 1 is not part of the domain. But the idea is, as x approaches 1, the function is going to approach this whole, right? So I don't know how the function is going to go. And it's from both sides. As you are around 1, the function actually is going to, the value of the function are going to cluster around this whole. Okay? So that's actually illustrated using technology. So how about we go to Desmos. Let's graph this function. So this is the function ln x divided by x minus 1. And you see here, let's zoom in. When x is at 1, it looks like the function is defined. We know that the function is not defined. So if you click on it, you see a hole, right? It's right there. When the input x is 1, the output is undefined, so the function is not defined there, but the values of the function get closer and closer to this height. And who's the height? That's 1. So the limit is 1. That's correct. Okay? All right. So let me erase this part. This would be the geometrical interpretation of this limit, right? Okay, part 2. So part 2, so this is not the limit that I promised you to do, which was this, right? So let's copy it and do it. So let's do that over here. Okay. So let's call this part 1 prime. How about that? So 1 prime. So the limit, this is still an indeterminate form of type infinity over infinity, because ln of x blows up as x goes to infinity and x minus 1 blows up as x goes to infinity. Okay, so I need to verify the conditions of of L'Hopital's rule. I need the function upstairs to be differentiable as x becomes large, and clearly the function ln of x is gonna remain differentiable. It's 1 over x, right? For all x that are greater than 0, and x minus 1 remains differentiable as x becomes large. So L'Hopital rule then can handle this situation. Let me change the color. So we get that by L'Hopital. By L'Hopital, we get that this is the same thing as the limit as x goes to infinity of the derivative of the guy upstairs. I'm not going to write all these anymore. So it's 1 over x divided by the derivative of the guy downstairs, which is 1. Okay? And the limit as x becomes large of this guy, this remains 1 over x. And this is how much? That's 0, right? As x becomes large, 1 over x becomes small. And again, if you go back to that software, the Desmos, you're going to see that eventually the function is going down to all the way to 0, right? This guarantees it. This reasoning here guarantees the behavior of that curvature. That it's going to keep going down. It's not going to go anywhere else. Okay? All right. So x-axis y equals 0, the line y equals 0 is a horizontal asymptote, as we said. Okay. Part 2. The limit as x goes to infinity, ex divided by x squared. Ex as x goes to infinity, remember how ex is graphed? The exponential function with base e. This is exponential function with base e. So clearly as x increases, the function is blowing up, right? So ex blows up, and also x squared blows up. It's the parabola, right? So both functions go to infinity as x goes to infinity, which means this is of type infinity over infinity. Can L'Hopital rule be employed? It can be employed as long as I verify the conditions. And I need to check that ex becomes or remains differentiable as x becomes large, and x squared is differentiable as x becomes large. Well, they are differentiable no matter what x is, right? Each individual one. And certainly x squared is not 0 downstairs, right? As x becomes large. So this is then, by L'Hopital, this is equal to the limit as x goes to infinity plus infinity of the derivative of the guy downstairs. Let me write it just this time because the derivative of ex is itself, divided by the derivative of x squared downstairs, right? Okay, and as we said, upstairs becomes or remains ex because the derivative of ex with respect to x is itself, and downstairs this becomes 2x, correct? So we get this. And this 2 downstairs, which is a half, it's a multiplicative constant, we can push it outside, but let's just keep it. Okay, so now we still have the situation that we had before. This is still an indeterminate form of type infinity over infinity, because that guy still blows up and that guy downstairs still blows up as x goes to infinity. So L'Hopital rule is going to be reapplied, and you can go over the justification of why the rule can be applied. So you can check the conditions that I was discussing. And if you apply it one more time, you're going to get this time a nice limit, because downstairs becomes simply 2, right? Upstairs is going to be ex no matter how many times you differentiate it. So downstairs is 2, and now this is simply infinity. Correct? Because that guy blows up, downstairs is a pure constant. So this is plus infinity. Okay? So that function at the end of the day is blowing up as x goes to plus infinity. Okay. All right, part 3. As x goes to infinity, find the limit of the function ln x divided by the third root of x. So what do we have an indeterminate form here? Yeah, this is infinity upstairs as x goes to infinity. This guy blows up and this guy blows up. So this is of type infinity over infinity. you can check that you can justify why the rule or L'Hopital rule can be applied. You can verify the other conditions, and once you apply it, you obtain that this is the limit as x goes to plus infinity of the derivative upstairs, which is 1 over x, divided by the derivative downstairs. Downstairs is x to power 1/3, right? So don't forget that this is the same as x to power 1/3. And if you differentiate that guy, you get 1/3 x to power 1/3 minus 1. And 1/3 minus 1 is minus 2/3, correct? So we get this. All right, let's do some aesthetic work here. So let's push this 1/3, this 1 over 1/3, which is 3, times the limit as x goes to infinity of this minus in the exponent means the reciprocal of that. So x to power 2/3 upstairs. If you take it north, you lose that minus. And then that guy, x is downstairs now, right? So this is the same as this. And how much is this? That's 3 times the limit as x goes to infinity. That's x to power 2/3 minus 1, correct? 2/3 minus 1, because the power here is 1. And 2/3 minus 1 is minus 1/3. Okay? And if you take it downstairs, you get that this is, as x goes to infinity, 1 over x to power 1/3. Okay? So now we've done some algebraic simplification from here to here, and now let x go to infinity. As x go to infinity, the third root of x blows up, and that guy 1 is a constant independent of x, so the whole thing is going to go to 0 then. So the whole thing is going to go to 0. So this function here has 0 as its horizontal asymptote, y equals 0, as a horizontal asymptote as x increases, right? So the end behavior is going to be the function is going to have y equals 0 as its asymptote. Okay? Okay, so part 4. The limit as x goes to 0, tangent x minus x divided by x cubed. Do we have one of the two types that L'Hopital can handle, meaning 0 over 0 or infinity over infinity? Well, as x goes to 0, tangent 0 is 0 minus 0, so upstairs is 0, and downstairs is 0 as x goes to 0, right? So this is of the form 0 over 0. You can check that the other conditions in L'Hopital's theorem, for the rule to be applied, are also verified here in a neighborhood of 0. And as such, L'Hopital kicks in and tells you this is the same as the limit as x goes to 0 for the derivative upstairs, and the derivative upstairs, derivative of tangent x with respect to x, that's secant squared of x minus 1 divided by 3x squared, right? 3x squared. And what's that limit? Well, as x goes to 0, secant of x, remember, secant of x means 1 over cosine of x. And as x goes to 0, cosine goes to 0. Cosine goes to 1, I'm sorry. Cosine goes to 1. So 1 over 1, that's 1 then. So this, as x goes to 0, this goes to 1. And 1 minus 1, that's 0 upstairs. And as x goes to 0, the guy downstairs also goes to 0. So I still have an indeterminate form of the type 0 over 0. So you can check that the conditions of L'Hopital apply upstairs for the guy upstairs and downstairs. So as such, we can re-employ L'Hopital's rule and obtain the limit as x goes to 0. The derivative of secant squared, that's 2 times secant of x times, I'm using chain rule, so 2 times secant of x times the derivative of secant, which is secant tangent. So I'm going to pick up another secant times tangent, minus 1, derivative of 1 is 0, and then downstairs I'm going to have 6x, right? So I'm gonna have this thing. Okay. As x goes to 0, secant of x goes to 1, as we just discussed, and I can split the limit as long as, so the limit of the product is the product of the limits as long as each individual limit is meaningful, right? As long as each one exists. So that's what I'm gonna do. 2 over 6 is 1/3. Limit as x goes to 0 of secant squared x times limit as x goes to 0 of tangent x divided by x. This guy over here is 1, right? So this limit exists. Now, if this limit exists, it means I can do this. I can split the limit as such. Limit of the product is product of the limits. So the question becomes, what is this guy? What is this guy? Well, as x approaches 0, upstairs approaches 0, right? Tangent 0, 0. And downstairs approaches 0. So this is of the form, this is still an indeterminate form of type 0 over 0. So we can check that L'Hopital can still be applied here a third time in this context, a third time, right? And we obtain derivative of tangent is secant squared, right? With respect to x here, so secant squared x divided by 1. The derivative of x is 1. And this is the limit as x approaches 0 of secant squared x. Well, this is something we just discussed. This is 1. Correct? As a matter of fact, L'Hopital can be avoided here, and we can use our knowledge of trig limits. For example, I could have thought about this. This is an alternative way to get this value 1. An alternative way. Tangent is sine over cosine, correct? So this can be, you can split that as 1 over cosine times the limit as x goes to 0 sine of x over x. Correct? One more time. Tangent is sine over cosine, right? And once you do so, I don't have enough room here. So so tangent is sine over cosine, and then the limit of the product becomes the product of the limits as long as each one exists. And we're gonna see that each one here is gonna exist. What's the value of this limit as x goes to 0? This is secant again, right? So that's 1 times, this is 1 too, right? So this is from Calc 1. As x goes to 0, this is 1. And at the end, this is also 1. So the same value that we found. Okay? All right, I'm going to erase this approach since we did it using L'Hopital's rule. Very good. So now putting things together, this is 1/3 times 1 times 1. So the answer is 1/3. So the value of this limit is 1/3. Okay? So this function here approaches the point 0, 1/3 as x approaches 0. So this function approaches the value, I should say, 1/3 as x approaches 0, which means the function is going to have a hole, right? It's going to have a hole at the point whose coordinates are 0, 1/3. Okay? So this point here is not going to participate in the graph of the function, this function, but it's a limit point. Okay? So it's a limit point. Because when x is 0, the function is not defined. All right. Moving on to the next one, part 5. Sine x, so as x goes to pi minus, so pi from the left, sine x divided by 1 minus cosine of x. Well, as x goes to pi from the left, sine x goes to 0, right? Sine x goes to 0. And the guy downstairs, as x goes to pi from the left, cosine goes to -1, right? This guy goes to -1 as x goes to pi from the left. Okay? So this guy goes to 0 as x goes to pi from the left, correct? And this guy goes to -1 as x goes to pi from the left, which means downstairs, this whole thing goes to 2 as x goes to pi from the left, correct? So this is then this is not an indeterminate form. Okay, so part 5, this limit is not doesn't give you an indeterminate form because upstairs goes to 0 while downstairs goes to 2. Okay, so L'Hopital's rule has nothing to do with this problem. And what do you get here actually? This limit is actually equal to 0, right? Because the function, this function is actually defined and is continuous at pi. So the value of the limit is going to be the value that this function takes at the point pi, at the point x equals pi. Okay, so if we go to Desmos, so the function here is, so y equals sine x divided by 1 minus cosine of x. Okay, and if you go to pi, which is approximately 3.14 or something, it's right there. This is the point pi. You're gonna see that the function value is actually 0. So the function crosses the x-axis at the point pi. Okay, and the function is defined there and it's continuous there. Okay, so L'Hopital has nothing to do with this problem. This is just so that you're aware that L'Hopital is not naively applied. Okay, if you actually apply L'Hopital here, you're gonna get an answer which is completely different. How about you check it? If you use L'Hopital here, let's write it and then erase it. So let's pretend that we didn't see this and we're mistakenly finding the limit using L'Hopital. Then the derivative of sine is cosine of x, and the derivative of the guy downstairs is going to be sine of x, right? Because that guy is 0, the derivative of cosine is negative sine. Negative times the negative becomes plus. And then if you find the limit, that guy upstairs goes to, as x goes to pi, this guy goes to -1, while this guy is going to go to 0, right? While this guy is going to go to 0. And it's going to go to 0 from the right, correct? Because you're not reaching pi yet, so sine is not gonna reach 0. It's gonna stay positive, but at the limit it's gonna reach 0. So it's going to 0 from the right, and that guy is negative upstairs. What does it mean? So what this means is this is actually gonna be minus infinity. So this limit is minus infinity, which has nothing to do with the right answer, right? So this tells you that L'Hopital, if you use it naively without even checking the conditions, is wrong. It doesn't violate the theorem, obviously, because the theorem is not applied there. You're applying it in the wrong place, and it gave you an answer which is not correct. But it's not the problems. It's not the theorem's problem. It's the application. It's a wrong place to apply it. Okay, because it's not applicable in this context. Okay. Let's introduce now a new type of indeterminate form. So suppose that the function f approaches 0 as x approaches a, and g approaches infinity, plus or minus, as x approaches a. Then it's not clear what the value of the limit as x approaches a of the product, if any, will be. So this kind of limit is called an indeterminate form of type 0 times infinity. Okay? So there is a fight between f and g. If f wins, the limit becomes 0, and if g wins, the limit becomes infinity. And if there might be a compromise between the two functions, and then this limit is going to settle at a certain finite number, okay, other than 0. Okay. All right. So how do we deal with this situation? Clearly, L'Hopital rule doesn't handle such a thing. However, we know that I'm gonna write something I'm not supposed to write, but just to illustrate the point, I know that such a situation, this is 0, right? Such a situation is 0. So you can think about 0 as 1 over infinity times that blue infinity. And this puts you in the context of infinity over infinity, which is the type of indeterminate form that L'Hopital can handle, right? So if you invert that guy, you get 1 over infinity, and if you then take the product, you get infinity over infinity, which is a situation that L'Hopital can handle. And another one, so you can keep the 0, and infinity can be thought of as 1 over 0, right? Again, I'm writing something that I'm not supposed to write, but I'm just trying to make the point here. So infinity can be thought of as 1 over 0. And then that 0 is here. 0 times that, I can think about it as 0 over 0. And this is a situation where L'Hopital can handle. So what I'm saying is, even though 0 times infinity, even though L'Hopital rule doesn't handle 0 times infinity, but we can convert the situation to actually force L'Hopital to help us. And that's what I'm saying. It's right there. So you can think about the product f times g as f divided by 1 over g. Or you can think about f times g as g divided by 1 over f. This puts us in the situation, either I'm going to have 0 over 0 right here, right? So let me zoom out to show it to you. So this guy upstairs goes to 0, so this is going to go to 0, and this guy downstairs is going to go to 1 over infinity, which is 0. So this puts you in 0 over 0, which is good for L'Hopital. And this one is infinity, right? Divide by 1 over infinity, 1 over 0, which is infinity. So this is of type indeterminate form of type infinity over infinity as x goes to a. So if you tweak that situation, then L'Hopital can help you, and it might be able to handle the situation. Okay, so let's take an example. Let's evaluate the limit as x approaches 0 from the right, x times ln of x. So clearly, as x goes to 0 from the right, this goes to 0, right? This goes to 0. And this goes where? Ln of x. Ln of x, where does it go? Just a second here. So ln of x, well, that's ln of x. As x approaches 0 from the right, where is the function? It's right there. It's blowing down, right? It's blowing down. So this guy is going to minus infinity. Agree with that? So we get this. And this is a situation, this is an indeterminate form of type 0 times infinity, the one that we just discussed. 0 times infinity. Correct? Okay. Alright, so let's tweak the problem, which means let's put ourselves in a context where I have 0 over 0 or infinity over infinity. The way I'm gonna do it is I'm gonna take the guy upstairs, which is x, downstairs, and as such I'm gonna have 1 over x downstairs, right? So I'm gonna keep that ln x over here, and the x times ln x can be thought of as ln x divided by 1 over x, right? If you divide by 1 over x, is the same as you multiply by x. So algebraically, they're still the same. What's the added benefit that this writing has? Well, if x goes to 0 from the right, this guy, as we said, goes to minus infinity, and this guy downstairs is going to go to plus infinity, which means infinity over infinity. That's still indeterminate, but of type infinity over infinity. And you can check the conditions of L'Hopital's rule are verified, and as such, L'Hopital handles the situation. So this is where L'Hopital kicks in then. And what do we get? Derivative upstairs, 1 over x. Derivative downstairs, negative 1 over x squared, right? Okay, and if you do the algebraic simplifications here, we get negative x, right? Negative x. And this is clearly going to 0. Okay? So you get to see through this example, even though I had a 0 times infinity type of indeterminate form, I was able to convert the problem to a problem where L'Hopital can be employed, and it solves the problem for us. Okay. Now you might think, oh, what if I take the 1 over the ln of x downstairs and the 1 over x keep it upstairs, the x keep it upstairs. So technically what I'm saying is, what if you think about this problem instead of thinking about it as the purple discussion? What if you keep the x upstairs and you bring the 1 over the ln of x downstairs like this, right? This puts you in an indeterminate form of type 0 over 0, right? Because as x goes to 0, upstairs goes to 0, and as x goes to 0 from the right, 1 over ln x goes to minus infinity, so 1 over ln x is going to go to 0. So this puts you in the context of 0 over 0, or indeterminate form of type 0 over 0. And L'Hopital can handle it, you can check. But the problem is, once you use L'Hopital's rule, meaning the derivative upstairs and the derivative downstairs separately, so you do this step here in this context, you're going to realize that the limit is going to get more complicated. So we wanna make the adjustment so that the limit becomes simpler, not more complicated. I strongly encourage you actually to try to do it this way and realize that the problem is going to become more and more complicated with this choice. Okay, so you're going to make the appropriate choice so that the limit becomes simpler, and in this context, this would be the simpler choice. Okay. Moving on to another type of indeterminate form. If you have a function f that blows up around a as x approaches a, and another one that also blows up around a, and you are studying the limit as x approaches that number a of their difference, then you have this fight. Both of them are infinity, but you're taking large number and you're subtracting another large number, right? There's this fight again between the two. And this type of indeterminate form is called infinity minus infinity. Okay? Let's take this example which illustrates the point. Find the limit as x approaches pi over 2 from the left, secant x minus tangent x. Well, as x goes to pi over 2, secant, which is 1 over cosine, right? 1 over cosine of x. Cosine as x approaches pi over 2 is going to go to 0, right? It's going to go to 0. And it's going to go to 0 from which side? Because x is approaching pi over 2 from the left. As x is approaching pi over 2 from the left, cosine is going to remain positive. And as such, this is going to go to plus infinity, right? Also, tangent x is going to go to 0, is going to go to infinity as x goes to pi over 2. But to which infinity? Plus infinity or minus infinity? Because x is approaching pi over 2 from the left. Well, tangent is sine over cosine. If x is approaching pi over 2 from the left, cosine and sine are both positive. And as such, this is going to become a positive thing. So it's going to become positively large. Okay? So this is a situation where I have plus infinity minus plus infinity. So it's going to be infinity over infinity minus infinity, which is an indeterminate form of that type. And as such, I need to do something about it so I can find the actual value, if that value exists. Okay. All right. So as we said, secant is 1 over cosine. So I have x is approaching pi over 2 from the left. 1 over cosine of x minus tangent, which is sine over cosine. Correct? So we get this. Let's have the same denominator. It's already same denominator. Let's glue them together. So we have cosine downstairs, that common denominator, and 1 minus sine of x upstairs. Okay? Now, as x approaches pi over 2 from the left, what happens upstairs? Where does this guy go as x approaches pi over 2 from the left? Well, sine of x goes to 1, so the whole thing upstairs is going to go to 1 minus 1, which is 0. Downstairs, as x approaches pi over 2, this is going to 0 too, right? So this is now this is an indeterminate form of type 0 over 0, and as such, L'Hopital can be employed. Obviously, you can check the other requirements for L'Hopital's theorem, which is both upstairs and downstairs functions should be differentiable in an open neighborhood containing pi over 2, which is clearly the case, and the guy downstairs should be the derivative of the guy downstairs should be not 0 in an open neighborhood containing pi over 2. Okay, and which is the case, right? Because the derivative downstairs has to do with sine. Clearly, there is an open neighborhood containing pi over 2 where sine is not 0. Okay, so L'Hopital is applicable here, so you can apply it, and as such, you obtain the limit as x goes to pi over 2 from the left. If you differentiate that function upstairs, that's minus cosine of x. And if you differentiate the guy downstairs, that's minus sine of x. Correct? Clearly the minus and the minus cancel each other. That's positive 1. Cosine x, as x goes to pi over 2, that function upstairs goes to 0. And that guy downstairs goes to 1. Correct? So you get 0 over 1, which is clearly 0. So the limit of this difference, even though it was an indeterminate form of type infinity over infinity, but this limit actually exists. It's a finite number. It's equal to 0. Other indeterminate forms arise from the limit, that limit that you see on the screen. So the limit as x goes to a, f of x to power another function g of x. The first case, if f of x goes to 0 as x goes to a, and the exponent function goes to 0 as x goes to a, this indeterminate form is going to be called of type 0 to power 0. Okay? Part 2, or case 2, if the limit of the base function goes to infinity, or is infinity, and the exponent function goes to 0 as x goes to a, then the indeterminate form that's going to be obtained is going to be of type infinity to power 0. Okay? And the third case, if the limit of the base function as x approaches a is 1, and the limit of the exponent function as x approaches a is infinity, then this indeterminate form is going to be called of type 1 to power infinity. Okay? Let's see an example to see how such situations can be handled. Let's take a look at this example. We would like to evaluate the limit as x approaches 0 from the right of the function 1 plus sine 4x. The whole thing is to power cotangent of x. So this guy approaches 1, right, as x approaches 0 from the right. Because sine is approaching 0, and 1 plus 0 is approaching, 1 plus sine 4x is going to approach 1. Okay? And cotangent, as x is approaching 0, cotangent is approaching infinity, correct? Why? Because cotangent is cosine divided by sine. Cosine divided by sine. So cosine divided by sine as x goes to 0, upstairs goes to 1, downstairs goes to 0, so the whole thing is going to go to infinity as an exponent. So this is of type 1 to power infinity, correct? It's of the last type, the third one. Alright, so let's see how we can handle. This is indeterminate of type 1 to power infinity. Let's see how we can handle this one. Well, what can we say about the base, the 1 plus sine 4x, this function? As x is approaching 0 from the right, well, sine 4x is gonna be positive, right? That guy is going to be positive if x is approaching 0 from the right. And as such, the whole thing is going to become positive, right? So that thing is, I mean, we know that this is going to go to 1. So, but what the point I'm making is that that's positive for sure. Okay? Then, what I'm going to do is I'm going to call this function, something. How about we call it y? Let's define this to be y. Okay? So, what's ln of y? ln of y is going to be ln of this exponential expression, right? Which means by one of the properties of logs, you can bring that exponent down, correct? And then multiply by ln of 1 plus sine 4x. Correct? And this is meaningful. This is meaningful. Why? Because that guy is positive. So ln acts on positive entities. So this is a meaningful thing. Okay. And why this is going to be helpful? Well, where does cotangent of x go as x goes to plus infinity? As x goes to 0? This guy goes to, as we said, this goes to infinity, right? As x goes to 0. How about this guy? How about this guy here? This goes to 1, and then this whole thing is going to go to ln of 1, which means it's going to go to 0, right? So we're going to obtain the form infinity, the indeterminate form of type infinity times 0. And how did we use to handle this? We used to take one of the two downstairs, right? I'm going to take cotangent downstairs. And if you take it downstairs, it becomes tangent, right? So technically I should have downstairs 1 over cotangent. And 1 over cotangent is tangent, right? 1 over the reciprocal of cotangent is tangent. So we get this. Okay? And now, what's the limit as x goes to 0 from the right of ln of y? What's that limit? This becomes the limit as x goes to 0 from the right of this entity, because that's ln of y. So of this entity. And that's of the form 0 over 0, right? We set the stage for that to happen. Let's check it. As x goes to 0 from the right, sine of 4x goes to 0. So 1 plus 0 is going to go to 1. ln of 1, 0. So upstairs goes to 0. Downstairs, as x goes to 0, tangent goes also to 0. So this is an indeterminate form of type 0 over 0, which means L'Hopital can handle. And once L'Hopital is employed, we obtained what? The derivative of ln, which means the derivative of the argument. And what's the derivative of 1 plus sine 4x? So derivative of 1 is simply 0. Derivative of sine 4x is 4 cosine of 4x divided by 1 plus sine 4x. So who's that guy? That's the derivative of, this is the derivative of ln of 1 plus sine 4x. Correct? Let's keep it in pink. And tangent, derivative of tangent, that's secant squared. That's secant squared. Okay? And what do we obtain? So that's the limit as x goes to 0 from the right of the quotient 4 cosine of 4x divided by 1 plus sine 4x times secant square x. And as x goes to 0 plus, the numerator goes to 4, right? Because cosine of 4x, as x goes to 0, cosine 4x goes to 1. 4 times 1 goes to 4. So the guy upstairs goes to 4. And the guy downstairs, well, we know that 1 plus sine 4x, since sine 4x goes to 0 as x goes to 0, this guy is going to go to 1. So this factor is going to go to 1. And secant x as x goes to 0 is also going to 1. So 1 times 1 is 1. And hence, the limit of ln of y as x approaches 0 from the right is equal to 4. But this is not what we wanted. We wanted the limit as x approaches 0 from the right of y, right? This whole thing, we called it y. What do we know? We know that the limit as x approaches 0 from the right of ln of y, we have the limit of ln of y as opposed to y, which is 4. How do we get our hands on the limit of y? So thus, the limit as x goes to 0 from the right of the function y, remember y is that 1 plus sine 4x to the power cotangent, is equal to the limit as x goes to 0 from the right of e to power ln of y, right? Remember what this property, exponential function with base e and log function with base e, they're inverse functions, so they undo each other if they are back to back, if you compose them back to back. So that's the same as y. That's the same as y. But I introduced this ln of y, the one I have, and from there on, it's gonna we're gonna be able to actually evaluate the limit. So exponential function is continuous at 0, so that's gonna be e to the limit. So the exponential function of the limit as x goes to 0 from the right, ln of y. And the reason I was able to bring in that limit is that because the function e, the exponential function e, is continuous at 0. And now we're going to use this green argument above to tell ourselves that this is actually a 4 here, right? So this is actually a 4 in the exponent, and the answer is e to power 4. So the limit of that function as x goes to 0 from the right, that limit is actually e to power 4. Okay. All right. Next, let's evaluate this limit. The limit as x goes to 0 plus, so 0 from is going to 0 from the right, of the function x to power x. So this is indeterminate of type 0 to power 0, right? Indeterminate of type 0 to power 0. It's the very first category here. Okay. How do we handle this? We can handle it the same way as we did in part 1. We can do it the same way as we did it in part 1. Let me do it a slightly different way. I'm gonna look at the function x to power x as follows. So if a is positive, I'm gonna use the following property. If a is positive, I can think about a to power b as e to power b times ln of a, right? If that base a is positive, so this is meaningful. A to power b can be thought of as e to power b ln of a, right? So I hope this makes sense. Let me explain why. This b right here can be taken as an exponent, right? Because of the ln, and then as such the e with the ln back to back, they undo each other, so you get back the a to power b. Okay, so I'm gonna put that here, and that's the property I'm gonna invoke at this stage. And as such, I can look at x to power x. By the way, x, the base x, which is playing the role of a here, certainly is positive because x is approaching 0 from the right. So that property can be applicable at this point, or can be applied at this point. So we get e to power x ln of x, right? So the b and the a actually are both x. So we get this, and same treatment as before. E being continuous, the exponential function with base e being continuous at 0, this is the same as e to power limit as x goes to 0 from the right, x ln of x. Correct? And if you pay attention to this limit, we've done it before. We've done this one before. Let me take you back there. It's right here. So we found that this limit is equal to 0. So the limit as x approaches 0 from the right, x ln x, it happened to be 0. So let's take this information. So this is 0 then. So what's the desired limit? It's e to power 0, which is simply 1. Okay? So the limit as x approaches 0 from the right of the function x to power x, this function is not defined at 0, but as x approaches 0 from the right, that limit is going to be 1. Okay? The very last thing I want to do in this section is I'm going to take you back to these the last three types of indeterminate forms we encountered. They all come from such a situation here, right? So the first one was 0 to power 0, second infinity to power 0, and the last was 1 to power infinity. You may ask yourself, how about this type, 0 to power infinity? As it turns out, this is not an indeterminate. As a matter of fact, I'm going to leave you with this exercise, and you're going to prove to yourself that that 0 to power infinity actually is 0. Okay, it's not an indeterminate form. Let's read the exercise. Let f be a positive function. Suppose that f of x goes to 0 as x goes to a, and g of x goes to infinity as x goes to a. So you have this form 0 to power infinity. And what you need to show is that this is actually a determinate form. This is equal to 0. So this limit is equal to 0. So I'll leave this as an exercise, and we'll discuss it in class. Okay? All right, so this completes this section.